Okay, so I would like to invite our next speaker, analyst. So analyst will to talk to towards the database identification of on vulnerabilities.
Okay, well, good afternoon, everybody. Thanks for being here. First of all, today I'm going to present you the paper. Now I'm going to present you the paper towards the database. It's part of my master degree thesis. And my supervisor, President Esquivel-Vargas. So we come from Institute of Technology. And yeah, let's start. So let me see what happened here. Yep, here you go. Okay. So basically, the proliferation of software have changed forever the function of modern societies, right? Not only in our studies and things like that, but also in supply chain, how companies work, and how we transport, how we communicate, right? So, and that is going to continue being that way. If we can see the chart that is the software market size basically until 2032, that is going to continue growing. That means we're going to have more software, more changes, right? That also increase the space for possible attacks. That means that we are going to have more possible vulnerabilities, more possible attacks, and the idea is to be ready for that. If you see the chart below, that is basically the trend of the known vulnerabilities number from the last 10 years. That means that the vulnerabilities has been increasing year by year, right? So that means that more software for the next 8 years, possibly we're going to have more vulnerabilities, right? So how we identify those vulnerabilities? Well, basically, there are two main stages in the software lifecycle in which we usually detect these, identify these vulnerabilities. First one is the development stage, right? In which we usually have accessibility to the code. That means we have the code there. We can perform tests, for example, static analysis tests. We can perform dynamic if we have a specific environment. Usually in development, we have specific environments like the code, and we can perform dynamic tests. We can also check for different libraries that we're using and analysis of those dependencies. And also without the production stage. That means that we don't have the code in a specific environment or we have a custom environment for ourselves. We're providing a release, we're providing code that is going to be used, we're providing modules to the industry. So at this point, we can have two types of vulnerabilities. The first is the zero-day vulnerability. Basically, the zero-day vulnerability means we don't have idea of what is happening there. We don't have previous knowledge of this vulnerability. It's going to be completely new to us, right? So the other is the no vulnerability, usually listed in CV, micro CVs, right? In which we have information about the vulnerability, information about which systems are the ones vulnerable to this. So this research is specifically focused on this field. Why? Because almost 82% of the vulnerabilities are not vulnerabilities. That means that we have knowledge of the majority of the vulnerabilities, and the need is ready for that 82%, right? Well, basically, to identify these vulnerabilities that no vulnerabilities is is going to help us prevent data breaches and other kind of exploits, right? But not only it's going to help us like to identify them, it's important to do it timely and efficiently because we have a vulnerability, for example, that it has been there for 10 years. The idea is to try to identify them as timely as possible, right? Not 10 years later. So also planning and efficiency is really important. And why it's important? Well, I think the most of you must know this, but it's important because that can have serious financial and reputational consequences for companies, people, countries, right? And we have seen several evidence of this in the last years in which vulnerabilities that are already known are exploited and create these kind of consequences. But what are the limitations and basically the challenges we have identifying those vulnerabilities? Well, basically, the first one is the manual and techniques of review. This means that the common tools we use for this, like vulnerability scanners, needs patches, right? Updates that are basically generated by programmers or engineers that update these tools. Basically, these update is manual. There's a new vulnerability. We go there, we understand what is happening, and we try to patch and add new features to our scanners for these, right? So basically, that means that a human is intervening in that process, right? Is understanding what is happening and is creating a patch. That is run to errors and delays, right? That that also generates a lack of stability and scalability. Why? Because it's manual, right? So we need to have too much hands if the vulnerabilities continue increasing. So basically, where we lack of that scalability, a lot of the vulnerabilities are going to come in the next years. For example, if you remember the chart I showed you at the beginning of the introduction, last year were more than 30,000 vulnerabilities. That means that we need a lot of hands to continue patching ours. And finally, vulnerabilities, the CVE descriptions, are written in a structured language. The principle is very constant once we write the descriptions, and we don't have a specific structure to write it. Basically, we can have different formats and words on it. And why is that a challenge? Well, we're going to see that in this slide. Basically, if we see the structure that is suggested by matrix, basically we have a problem, right? I'm going to read it as is. Problem in a specific software name, all name, and version. That's the impact when it is. So this that is the proposed structure, but not necessarily the CNAs or ones that publish this CNAs are going to follow this structure. And we have two examples. In we below, we have two examples of possible CVEs, right? If you see the one on the left, we have it has an internet divider, and that's not the problem. Starting from it or first part, right? Then we have a machine of different models and the versions that are you can see there, for example, Apple creates because fragmented old version lower than and the version down, right? Basically, what we have there is that software conversion, but CDs are one to many. That means that I can have one CD with multiple devices or software that are vulnerable to that vulnerability, right? So in that case, using several names with several different versions. So imagine that for a computer that is trying to analyze and create automatically scanners is really difficult just by using normal code, understanding this structure because it's unstandardized and it's written by humans, right? I mean, we see the other city, they understand that you just go straight forward with the software data, right? And then there's any indicator of that the machine version is virtually done to the to portray, right? It's just the context and redaction that string that is constantly by that subversion. We as humans read that and we understand like a little bit his finger. But there are greater difference between that version and for example that is part of the name, right? That is- So knowing that and seeing the comparison between these two series, what we're going to try to solve with our proposal is to identify this kind of things easier using slides. Here is our proposal. Basically, all right, and it's told to make the identification of vulnerabilities, non vulnerabilities using artificial intelligence techniques, particularly pre-trained large language models. GPT, right? In case this example, this proposal will use GPT. So why pre-trained models? Because they're really good at understanding natural language, right? So that's the idea. Because the problem itself, it's a context of the description problem, right? So that's the reason why we propose to use this. The idea is to leverage the models. So I don't know education that is going to help us scale because we're not going to need more patches. Because in the case of a human, we read the description and we create code. In the case of the proposed that we're going to do, the model itself understands the natural language, so don't require patches all the time. And the idea is to improve the accuracy and reduce the false negatives. For the representation, we're going to get more into detail why negatives are so important in this. Well, basically, this is our proposed architecture. We divided the architecture into big stages. The first stage is the feature structure stage, in which we construct that software name and version that is vulnerable. That is really what is important of the CD when we're trying to define. And the other section is the validation stage. But before getting in more detail about the architecture, we're going to explain how we're going to implement this and why we're doing it that way. Well, basically, we have two possible approaches. The heuristic approach. The heuristic approach basically is if I am a fun and I don't have AI and I'm going to create a program to extract that information, I need to do it using code first. Uh, Python, I'm using regular expressions and if commands and things like that to start grabbing the information from the text, right? You need a structure to do that because if you don't use a structure, you have a lot of possibilities, right? So we base our linguistic implementation in the proposal that writers give us for the structure of an structure. So basically, using normal code, we created a program that is able to extract information and divide the description into specific steps. How we usually do that? Well, basically, grabbing like versions, things like that, and dividing all the description. This is the heuristic approach that we are going to compare that with the GPT approach. Basically, the GPT approach is that we are not going to do anything as humans, because as we saw in the introduction, that manual interaction with humans is a that is from the left, from to error. So GPT basically is going to receive a prompt and it's going to do it for us. So we're going to try to see what that happens. So the proposed architecture. In the proposed architecture, we're going to go first in the feature structure stage. In that stage, we receive the CPEs in CSV format. Basically, we pull that from the Microsoft repository and in raw text, pass that to a model we call the signature generation model. Because what we're going to create is signatures, right? Basically, server name, server vulnerable version, and the comparator. And then we're going to start store that in a database. That is basically a signatures database. Let's talk about the most important model of this stage, that is the signature generation model. Basically, this model is going to extract those signatures. That means that it's going through the description, finding what is the string, what is the version that is vulnerable to that server name. But like when we go back and we remember the description we were talking to, there are certain cases in which say something like all versions lower down, right? So the signature not only is going to have the versions that are low, but also it's going to have a comparator, right? That's done, lower down, equal, and that is going to help us identify all the versions that are really vulnerable. Because the CVE really just tells us comparator. Is that or all, I don't know, like lower than that or before that, right? And also that structure of information is going to help us like convert the unstructured text created by humans to a structured text in format. That is a lot more easier to read for systems, right? Because it's a structure and the key value system is going to help us. So we have two implementations for this stage heuristic and the limiting one. We're going to start low risk. Basically, we process text, because we, as a machine, usually need to process text, we need to delete this in words, where they're really going to be useful for this, as you remember in the structure, like the CDE, the attack, and the cost will the virus was in this approach. So what we want is to filter all the possible text extractions, the vulnerable versions, vulnerable links. Then we once we have that identification, we're going to create this JSON that has that information. And with that information, we're going to create a new record in the database. So basically, we have that cycle in which we're filtering the text that we really don't need, right? And we're creating this JSON that we really need. So we have things like separate comparison symbols, place comparison symbols that have processing general expressions, and Python libraries that can host this. But basically, this manual code libraries. And if you see the difference in the models is a lot more simple because we're basically sending the description to a GPT 3.5 turbo model in a branch. Basically, you have a prompt in which we say to the system, we have the description. I want you to extract the model names, so and the normal questions, right? So and the comparison symbols that we can use. So we provide probably an example. We provide the skill that we want to utilize and we spec something important is that we expect a result in JSON. So basically all this going to respond us in a structured way. It's not going to respond us in another unstructured text. We specifically set to the prompt. Please return us a structured JSON for the example. So that's what we expect. A lot more simple, right? We're just asking questions. Now that you understand the feature structure stage, we are going to proceed to the validation stage, right? So basically, the example that I did in the identification stage is to validate if the signatures we graph really in comparison to a specific software version that we know is vulnerable, if it is going to let the right. So in case of the risk, you have the operations again. In case of the risk, where the way basically comparing the modules in the database, and then we compare the signatures to the ones the user is using as a input, right? And it tells us yes, it's vulnerable or not. In case of the GPT model, the same, but instead of using comparison of strings, things like that, we just send the prompt to the GPT model. For that, we created experiments. The first experiment is basically populate the database. How good are the models populated the database? Well, basically, we analyze basically all the CPUs from the year 2023. 39,000, more than 39,000, excluding the reserved ones and the reject ones that really don't provide any important information to us. And something important in this experiment is that for us, a true positive is that at least per CV, we have one signature. Why? Because the reason why CV exists is because that witness was exploited and was trying to come up with an ID, right? So at least one system, or at least one software entity, one little version needs to exist in a CV. Why for us, the positive is the model was able to at least get one signature transcription. These are the results from this experiment. Basically, GPT model was able to extract at least one signature for every one of the CVEs that we tested against the heuristic model. That was not the case. In basically half the cases, 43.9% wasn't able to get that right. And also in accuracy, I have one score that the GPT model performed better than the heuristic model. If we go to the execution times, we can see that the heuristic model is faster. Well, basically, it's faster because it runs in log in the code. And in this case, we use the OpenAI API and latency in the connection for the prompt in the response. It's the reason why the model is slower. But possibly, if you have a specific cluster in which we can run the model, it will be faster. It will the then we got this other experiment that is a vulnerability identification experiment, in which now we're going to test, okay, with the data that we generated, are we really able to identify if a software is vulnerable or not by using this approach? Well, basically, in this case, we randomly select 383 CVEs from the list of 2023, and we generated 600 cases. Why do we have 600 cases out of 383 CVEs? Well, because we can generate two possible cases per one, right? It is vulnerable or not. And let's say I have a description of a CD in which a specific software product is vulnerable. Well, I can create a case, the name of the product with different versions, one vulnerable or not, and we can create several cases out of just 383 CDs, right? So that's the reason why we have more cases than CDs. Something important here is that a true positive for us is a software name version is really input in the system indeed is vulnerable to a CVE, and the system indeed tell us, yeah, it is vulnerable. And a false negative for us is when it's vulnerable, and the system tells to us, no, it's not vulnerable. and we have misinformation there because we are vulnerable, and the system is telling us, no, you are not. And that's the worst case scenario for a vulnerability identification. Why? Because we have misinformation. Imagine you have a illness, let's say, and you go to the doctor and the doctor tells you, no, you're okay. You don't want to be sick, and the doctor, it's okay, right? So it's really important for us to avoid false negatives. Let's proceed with the experiment results of this part. The result is how good you are really detecting positive. And as you might see, the result is good and good at. Why? Because also has a lot of false negatives, right? And if the reason why it has a lot of false negatives, it is because the system really don't know how to say, yeah, we're not vulnerable or you're vulnerable and indeed you are, right? So that's the reason why you know false negatives is important in this experiment. We got to acknowledge that we are vulnerable and the activity model was really good. Basically, using 94.6% of it was basically correctly saying we're vulnerable and we're not. And in this case, we really use the misinformation. So correction code is the most important metric because unfortunately, with misinformation, tells us which we are vulnerable and always that important. Accuracy, well, basically, the repeatable model was also more accurate than the heuristic model, and also has a more balance in everyone's score. So, thanks to these results and the previous experiment, we can say that the GPT model behaves better in this kind of experiments than the heuristic. Well, let's talk a little bit about conclusions. We prove that AI in this specific case, GPT trigger models is capable of identifying vulnerabilities by just using the description, the text description, right? And well, in the data that we're going to use this are also, yeah, we're able to prove that that means that the model is capable without trying because we don't need any kind of return and without fine tuning. That's something important. Basically, the model has skills and the capacity for the model have to understand the natural language, help us do it without grades. Also, not was able to do the funnels. Exceptional accuracy with errors of, and if you may remember, and I told you that a lot, that all is the most important for us, and a balance. So basically, the model behaves really well without this kind of fine tuning or things like that. And finally, for us, one of the important contributions is that once, as a lot of papers that have been presented during this workshop, AI proves to be good for cybersecurity, thanks, for example, identifying CVPs, and can help us a lot in the future to continue doing research, to continue understanding what we can do with this kind of tools. So, thanks. And you have the search topics available with that QR. And yeah, this is the space for question. Thanks.
Thank you very much for the presentation. I have to go to the please question. Okay, almost just said that.